So, when we first encountered the concept of interference, back when we were talking about mechanical waves on a string, we said that the total amplitude, or displacement, was given by the principle of superposition, which says that when two or more waves overlap, the resultant displacement at any point, and displacement is kind of general word used here. The displacement at any point and at any instant is found by adding the instantaneous displacements that would be produced at the point by the individual waves if each were present alone. Superposition, right? So that's kind of like a weird way to just say that you add the amplitudes. So it's like each of the waves, whatever their amplitudes at that point would be individually, you just add them up, right? At every point. And this turns out to be true for electromagnetic waves as well. And the word displacement, like I said, is a little bit more general in this case. It refers to the amplitude of the electric or magnetic component of the electromagnetic field. The electric component is much, much larger, so typically you'll see treatments that just ignore the magnetic component and just treat the electric component for that reason. But in any case, for waves on a string and longitudinal pressure waves that we've studied before, we were pretty much only considering waves along a single axis. And we studied them in such a way that we wanted to illustrate what happens when counter-propagating waves, like sound waves or pressure waves or mechanical waves on a string, what happens when they interfere with each other in counter-propagating. So, one's going to the right, one's coming back to the left, and they overlap. And we saw that it creates a standing wave where there's nodes, where there's no net wave, and there's antinodes where there's maximal displacement. And you kind of have this breathing system where you have those nodes and antinodes, right? So you might have these components here. This would be a node, antinode. Nodes are where they don't move. Node. And so then, at like another instance, this might be down here like this. So we studied those systems before. Well, now we're going to consider a wave source in 2 dimensions, right? Because this is only 1 dimension here. We're going to consider one in 2 dimensions. And I'm going to attempt to use this circle tool and hopefully be able to draw some concentric circles here, because we have the source and we have, if I'm describing like wave crests, we have these wavelengths that propagate radially outwards like this, and you'll have to imagine that these are all perfect. That one was pretty good. All right. And imagine those are all equally spaced. So we have a wave propagating outwards, right, in all directions. And it's now in 2 dimensions. Okay. And I'll illustrate that the difference here between the lines is supposed to be wavelengths, right? So let's call this source 1, S1. So this is a source, right? A wave source in 2 dimensions. The wave fronts, they propagate radially away, and they propagate at wave speed, frequency times wavelength. It's a sinusoidal monochromatic source. And monochromatic, as we had just discussed, wavelength is not changing, and the laser is the best way to accomplish that. Lasers aren't perfect, but we're going to consider this an ideal monochromatic sinusoidal wave. All right, so now what happens if we bring another same source, identical source, nearby? The radially propagating waves will interfere. And it's not going to be a really simple one-dimensional thing where we create, nodes and antinodes along one dimension. It's going to be a more complex situation. So bear with me, but I'm going to attempt to do a decent job doing this. I think, yeah, okay. I'm going to attempt to kind of draw this. So we have our first source. Let's place it here. That's your S1 that we just drew. And it's going to radially propagate. So there is energy that is moving along the disturbances that we're describing here. Right? It's going to be kind of a cool picture when we bring the other one into view, if I can do this well enough. Certainly won't be perfect, but all right, a few more. Okay. That one's no good. Okay, so that's one, right? Now we're going to introduce another source along this, I guess, would be y-axis. Let's do it right here. Well, let's do it further down, so it's a little bit more symmetric, about right here. So S2. And I am, of course, going to do the same thing, because it's an identical source. So to the best of my ability to quickly do concentric rings, I'm going to put one between there. We start to see locations of overlap of these rings, which are representative of displacements not doing this one nearly as well. There we go. Okay. Darn. Alright, more aggressive with it. Way out here. Okay. Okay. So, maybe you can see some regions. This obviously won't be perfect, but maybe you can see some places where the interference is happening here, right? So yeah, so we can identify some points here. So let's pick a point, let's pick this point here, and we'll call that point A. And I picked that point on purpose. It's along that axis, that x-axis, where there's a blue and a green line overlapping, right? If I were to have drawn this perfectly, they all would nicely overlap exactly on that line. They don't look exactly like that, but if you this is like one of those, I don't know what they're called, but when you relax your eyes, you start to see a picture form, and it's like this, like optical illusion kind of effect from like that they used to have on posters or magazines or whatever. there you can kind of, if I've drawn this well enough, and the one in the notes is slightly better, but you can kind of relax your eyes and start to see kind of like patterns sweeping out, like along where they're interacting. If you kind of notice certain regions that are more uniform, so that's kind of like what we're going to start to see more explicitly. So let's pick this point. Let's pick this point here. We'll call that B. And that's another point where they overlap, of course, right? And so for both A and B, so these distances from each source, from source 1 to A and source 2 to A, of course they're drawn very much not to scale, so forgive me, but if they were drawn better, those two distances would be equal, or they're supposed to be equal. If I were to have drawn it a little bit better, or picked my points better maybe. And so what that means is that the waves arrive in phase. And so therefore the total amplitudes at any given time at that point is twice the amplitude of each individual wave. And point B is a similar story where the distances are not, they're not equal. They're not supposed to be equal even in this one. But they're we'll say a wavelengths multiple of each other. So the distance from the second source to point B is exactly, we'll say, 3 wavelengths greater. Maybe it's a little more than that, I don't know. But pretending I drew this diagram well enough, it's some integer multiple of wavelengths greater. And so that means that the two waves, again, arrive at point B in phase, just like they did for A. There's a little bit of a, delay for B versus A from source 2, but same situation happens. So a wave crest from S1 arrives at B exactly, a few cycles earlier than a crest emitted at the same time from source 2. And in general, if waves from any number of sources, right, arrive at any point in phase, the resulting total wave is the sum of the amplitudes of the individual waves that overlap at that given point. And this is called constructive interference. So, constructive interference. Right? So, if waves from any source arrive in phase at a given point, constructive interference. So for it to occur, the path length difference is really the important thing. The path length difference between the two sources must be an integer multiple of the wavelength. So, like, if if this is like R1 and this is like R2, right? R2 minus R1 must be equal to some m integer multiple of the wavelength, right? Where m could be 0. In the case of point A, it is 0. Could be positive or negative, and any integer. Okay. How about point C? So let's pick another point where the integer multiple is not the same. Let's pick a point where it's drastically different. So here, the green source, we're on a line, but we're exactly halfway in between a blue source, right? So what that means is they arrive exactly out of phase. So the path length difference between these two lengths at, we'll call this point C, for each source is exactly out of phase. And the resulting amplitudes for the combined waves is actually equal to the difference of the two individual amplitudes. And that's called destructive interference. So I'm going to write that out. Destructive interference. Yeah, so if waves from any source arrive, I'll say not in phase, because it doesn't have to be exactly out of phase for it to be destructive interference. It's just anything that isn't exactly in phase is out of phase, and therefore destructive interference. A given point, you have destructive interference. Okay. And we would say R2 minus R1. So destructive interference occurs total destructive interference, at least, is when they're exactly out of phase. And it's the same situation. If you have integer multiple m, total destructive interference, total, is when they're exactly half out of phase. But like I said, even if they're not exactly half integer multiples of the wavelength, it's still destructive interference. Anything that isn't constructive, completely constructive, is destructive. And so I'll say, in this case, amplitudes add. And for destructive, amplitudes subtract. For destructive. That's kind of the key there. And there is such a thing as a antinodal curve that identifies all of the points of constructive interference. And let's see if I can paste this in, maybe. Maybe not. All right, my tech isn't cooperating. It's gonna just look something, and don't check it because it's not gonna look exactly like it, but it's gonna look something like this, right, where that's symmetrical. And same thing over on this side. Something like that. So kind of like what I was saying before, where your eyes kind of see these like lines where there's overlap. That's what those lines would translate to as the antinodal curves. And so if my diagram was perfect, and you can look at one that's computer generated and better see, but yeah, there's lines that all the points of intersection line up. All right, and to connect this back, these are analogous to the antinodes and standing wave patterns that we saw before. But it's really important to note that interference patterns, they're not standing waves here. So in standing waves, it's caused by the interference of the two counterpropagating waves, and you have this standing situation where the amplitude kind of rises and falls, but the disturbance does not travel. There's no net energy flow in either direction. Whereas here, if we were to animate this, if we were to, let time, push go on this movie here, these concentric rings would be propagating out and out and out and out, and you wouldn't have, standing energy. The interference patterns here, they do describe a net flow of energy outwards from each of these two sources. The the antinodal, the interference pattern just describes the spatial distribution of this energy as it kind of flows outward. So it kind of like describes like the channels along which the energy is concentrated is kind of the thing. All right, next we'll move on to some slit experiment descriptions.